Greetings. We're going to start Chapter 12, Kinematics of Particle Motion under Constant Acceleration. Now, hopefully for many of you, this is going to be, in fact, all of you, this is going to be a major review. Where you should have first seen this would have been in a physics course prior to coming to UNB, and then in Physics 1081, you would have gotten a healthy dose of this. So this is actually just a review, so there's a limit to how deep we will go into this material. So just to start things off here, the key to this is acceleration is constant along a path. So now normally you've used constant acceleration equations with respect to projectiles, so you're looking in the y, you have constant acceleration due to gravity, okay? We are going to wind up expanding that a little bit to where something is on a curved path, and we will have an axis that goes along the path, and as long as the acceleration is constant along the path, you can actually still apply those equations. So, but that's a little ways away yet. So very quickly, just to go over, where do these equations come from? Principally, we need to be aware of the Newton's second law, F equals ma, where we're saying acceleration is constant. That would mean, and if it is constant, and we're dealing with constant mass, it means the sum of the forces would be constant as well. So acceleration, we know, is dv dt, and I'm going fast here because you should have all seen this already. If we integrate acceleration, since acceleration is a constant here, that just becomes a times the quantity t2 minus t1. But acceleration is also dv dt. We can cancel the dt's and we get v2 minus v1 here. So this is the familiar integration, all right? And this is the common form that you've probably seen before. Something like this in physics. This may be v1 plus at equals v2. Here we have v0 going to v1. This is the 0th state, this is the first state, and we can number these any way you want. All right. Now, just to take a little look at this, if we multiply through here by mass, what would we have? This equation would be, I'll go down a little farther, mv0, okay, plus mat. Now, but what is MAT? MA is the sum of the forces. So I can re-substitute that in. So I have mass times initial velocity plus the integral of the forces equals mass times velocity in the second state, in this case labeled 1. All right, this is the momentum equation, which hopefully you've all seen before. All right, so this equation here that you used is nothing but momentum. And what I want you to notice is that it relates acceleration, time, and velocity. We're going to see, we'll have three constant acceleration equations, and so they all are based on whatever a is, and then there's two other terms. So what they do is allow you is knowing, say, a and t, you get v, or knowing a and v, or knowing a and t, you get v, knowing a and v, you get t. All right, and so this, our ability to relate things is going to be, as we do other equations, will be changing. Now, if we integrate this here a second time, going from velocity to position, we get, say, the form you've probably seen this before is in terms of height under constant acceleration of gravity. Height equals the initial height you're starting from plus the initial velocity times time plus 1/2 at squared. So this is another equation, and this one relates acceleration, time, and distance. So knowing a and d, you get t. Knowing a and t, you get d. That's useful. All right. Now, the third equation that you've typically seen, the way we get that is we need to integrate along the path. So if you say, if we look at acceleration in the y with gravity, the path, the vertical path, so if we integrate with displacement as opposed to time, so a, y1, y2, we'll note, and a is a constant, so all we'll get is a times the quantity y2 minus y1. But a is again dv dt, And so what we can do is move that t over and shift the order, so we get dy dt, which is nothing but velocity dv, so we get this form. It's kind of a slick trick. Okay, well, if we integrate that, we get this equation, a y2 minus y1, because a is constant, so that's simple. And then we have integral of v dv, which is v squared over 2. Bam. And we can rework these things, multiplies the 2, and we could have, bring the 1 to the other side, we'd have 1 half v1 squared plus ad equals 1 half v2 squared. Okay, where d is the net change in displacement, y2 minus y1. Well, let's multiply by m again. And of course, this is also the form you've seen it. V0 squared plus 2ad, that's just clearing the 2, equals v1 squared. But staying with our original form here, if you multiply by mass, you get 1 half mv squared plus mad equals 1 half mv squared in the second state. Well, what's this? This is kinetic energy. And this is the work done. So ma is the sum of the forces times distance. Force times distance is work. So our initial kinetic energy plus the work done by all the forces equals the final kinetic energy. This is nothing but the energy equation, which you've seen before. So here we have recognizing that. So these equations are useful for estimating projectile motion, which you've done before, gravity in the vertical. But note there's no force in the horizontal, so whatever velocity we have going across, moving this up, whatever velocity you have going across, we presume we're in a vacuum and the velocity never changes. So you'd apply these equations in the y, this is what you're used to doing, and then you just, velocity times time is distance covered in the horizontal. So these are the things you've seen before, and so we're going to practice some projectile problems. And I'll note as we do these, you will have on your final exam a constant acceleration question. The exam is normally, I believe, 7 questions, and one of them will be a constant acceleration question. I want to comment that this is typically the lowest scored problem on the final exam. Students tend to just look at this thing and go, oh, it's constant acceleration, I know it, and they treat it like a 3-foot putt in golf. And so they don't practice them and develop the skills to solve them. And I give very simple problems on the final, and it gets blown. I will comment something. There's probably many of you that are here that'll listen to this that went to high school at FHS in Fredericton. When my kids went to school there and went through physics, and when you do this course as long as I have, it becomes hard to come up with new questions. And so for years, I actually would go and get homework questions on constant acceleration from FHS. There's one of the instructors there is very good, really pushes the students, and so I would take one of his problems and put it on the final exam. And so what you're looking at seeing on the final exam is nothing more than a high school constant acceleration problem. And history says it will be the lowest graded problem on the exam. It is consistently. All right? So, I encourage you, pay a little attention as we go through this material. You will see it again.